All right, kiddos, hello and welcome. I should figure out a way to start these videos, shouldn't I? Otherwise, it's going to be annoying every day. All right, kiddos. But anyway, the one I posted for you guys earlier was a repeat from, I think, 2 years ago. We are needing to get into section 9.3, though. I think I have that homework due. I need to make a paper planner. Oh, there's my calendar. It's behind you guys on the screen. Homework section 9.3, we are skipping 9.4, going to 9.5. It's going to look a little weird on your calendar. Hey, speaking of which, you guys can be looking at your calendar still. I'm still trying to keep that up to date, and if you notice, this calendar is crazy packed, but that's because it has all of my different classes in there. However, if you guys notice if you go look at our calendar via class resources, Google Classroom, should know how to do that by now. You guys can look ahead because in Google Classroom, I only have assignments popping up as it's kind of time to start them. Instead of having them pop up though at 8 a.m. in the morning, getting ready for us meeting in class, I'm gonna have them popping up 9 p.m. the night before, just because some of you guys, it might be more helpful for you to see it before you go to bed to kind of think about the next day and how you plan. I'm gonna try to give you guys at least a couple days to do homework normally. Section 9.2, technically, let's see, today is Tuesday. It's gonna be a little weird because I'm recording before you guys are mostly watching these, but section 9.2, I think I gave you until Thursday to get that turned in. That's what the calendar shows. Then section 9.3, I'm getting these videos up for you tonight, which is Tuesday night, but you have until Friday to finish. Check out the announcement in Google Classroom about Edpuzzle and why I'm doing lectures through that. But I want these videos to be concise. I want them to be short, sweet, to the point, so you guys can get the information. I'm not going to let you guys do double time or skip ahead in them. So you are taking notes. You are taking notes like normal. There's going to be a big old fat note check at the end. But anyway, all these announcements are being put in Google Classroom. You guys just stay up to date on the feed. I'm going to try not to spam you. Just putting out information that is helpful. So pretty much if you check by 9 p.m. every night is what my goal is. If you check by 9 p.m., the assignments for the next day or 2 or 3 should all be up. Any Edpuzzles, any lecture videos, and any homeworks, as well as the due dates. But as you guys already know, in Google Classroom, if I can get this hidden real quick, there we go. In Google Classroom, you can see what's coming up as far as section 9.2, the Edpuzzle and the homework due on Thursday at 8 a.m. And then I'm going to have section 9.3. I think there are 2 Edpuzzles for that. One interesting by heart video that I think is super fun, and then the one that I'm making right now along with the assignment due Friday at 8 a.m. So I'm keeping that 8 a.m. just because, I don't know, you guys are used to it, we've been doing it all year, but just letting things show up a little bit earlier as far as 9 p.m. the night before. Anyway, I love you guys, I miss you. I'm going to be having live math lab hours during our normal class time, but I'll be going ahead and posting that as an announcement in Google Classroom. And so once things really start, which is tomorrow, you'll have content just popping up as far as assignments and lecture videos to watch, and then I'll just be chilling in front of a camera pretty much in a live Zoom session is what it's going to be, but there's going to be a link that you guys can get to it. I can get out of this screen, you guys don't need to see it anymore. But I'm going to be chilling and available if you guys have any questions, if you have any homework questions, any clarifications. I mean, you're going to be able to see the evens to everything. And so since you're going to be able to see the evens to everything, you don't necessarily need me doing that via a video or me forcing that on you via a video. So that's just something where, oh man, this is working so much better than yesterday. You should have seen the Calc AB video. Anyway, where was I at? Oh, trying just to make the videos that you're forced to watch only be like the short, sweet version. So today was a little bit longer. I was introducing a lot, but otherwise, I'm just going to be kind of popping in here quick and saying, let's go, and let's go with the content. But if you guys want to come and see me, come into the math lab, which is approximately our normal class time. It's going to be every weekday until this thing is over, unless for any reason I need to cancel or I need to reschedule. So yeah, check me out in the live Zoom session, normal class time, every day starting tomorrow, which is Wednesday, or maybe starting today if you're watching this on Wednesday. So here we go. Let's go ahead and go over section 9.3, geometric sequences and series, not like the arithmetic. I learned this from Khan Academy, actually, because I was showing my Algebra 1 kids the beginning of statistics. You guys should have done section 9.2 already with the video I already posted from a couple of years ago. Arithmetic is the noun, like what you learned when you were in elementary. Arithmetic is the adjective. Anyway, good to know. I thought it was arithmetic, but that didn't make sense in my head because it's spelled M-E-T. Anyway, arithmetic. But we're going to geometric, so much easier because everybody knows how to say it. So geometric, what's different? It's another special type of sequence, except this time, instead of it being addition or adding a constant every single time, this time we are going to be multiplying by the exact same number. Remember, it's not about just there being a pattern, but there being a, ready, common or constant. Common or constant. I'm going to go ahead and write constant to get it ready down here. A constant pattern. And this time our constant pattern is a constant multiplier. P.S. If these videos ever go too fast, please realize that I am trying to not waste your time. So if these videos go too fast and you're trying to get your notes down, if at any point I'm going too fast, I would rather go too fast than too slow, since you guys aren't able to skip ahead or double time me. So feel free to pause me, feel free to go back, rewatch. That's not going to mess up your progress. You can skip ahead to wherever you left off. That's totally fine. Just wanted to let you know I'm going to not wait for you to write down notes, because you can pause and you can take that time if you need it. Once again, keep taking notes. All right, table of contents, all that jazz. So as you guys are looking at this, if R, well, D was our common difference from section 9.2. So in this one, R is going to be our common ratio. And that common ratio is going to be, sorry, I apologize, that was messy. R is going to be the notation for that common ratio. And so what another way of describing that would be is constant multiplier. R is the common ratio. That is the actual terminology for him. It's also known as the constant multiplier, but how do we find that R? Well, you see it up above here in that A1 to A2, A2 to A3, A3 to A4. Just that pattern will continue. But the way you find it is that with the little formula that you see right there. I can zoom out a little bit if that helps. But we're going to find it by basically taking any A sub n, which is a future term, all over an A sub n minus 1, which is its previous term. If it's the 10th, it'd be over the 9th. If it's the 4th, it'd be over the 3rd. I can just take any division, and if this is truly a geometric sequence or series, then that division should always get you to the exact same number. Moving on, in our discovery, here's an example of a geometric, there we go, a geometric sequence. Remember, sequences are separated by commas, series are separated by addition. So this geometric sequence, hopefully you guys can see it pretty quickly, in that every time the value is just doubling, starting at 3 and then it's doubling. By doubling, I mean multiplying by 2. Not squaring, just doubling. Multiplying by 2, multiplying by 2, multiplying by 2. Is this geometric? Yes, because I can identify a common ratio of 2. But if I want to go to the 10th term, as we talked about in previous sections with these guys, yes, I can find a pattern, and when I find that pattern, I can go ahead and continue it however many times I want, but that gets tedious, especially if we're trying to do something like the 100th term. So we love these little formulas. I already have it up here so you guys can see it. We love these little formulas that let us jump. Just the notation is a little weird with the A's and the subscripts and the superscripts. So just to make a little bit more sense of what's going on, if you guys notice, to get to the 48, I think I kind of did this in the arithmetic one from yesterday. To get to that 48, one way is, yes, to jump 4 times that multiplication of 2. The other way is we could have started at 3 and said, okay, wait a minute, we're starting at 3, and then where are we going from there? Well, we're going to go ahead and multiply that 3 by, ready, 2 to the power of 4. We're going to take that 3 and say, hey, I want 3 times 2 times 2 times 2 times 2, or 2 to the power of 4. And if you notice, this 48 is actually our 5th term. And maybe some of you guys are starting to see where this whole formula down here comes from, as far as we're always going to start with the first term times the common ratio, whatever that number is, that common multiplier, that constant multiplier is being multiplied over and over and over again, that common ratio to the n minus 1 term, kind of like we did with the arithmetic ones or arithmetic ones. Stink, I have to get that right. So we're getting to the 5th term, and we're getting to the 5th term by multiplying 3 by 2 to the power of 4, 1 less than the term that we're on. So in this one, it's easy cheesy if we understand this formula, or even understand just the idea, in that to get to the 10th, I'm going to start with the first, which is 3. I'm going to multiply it by how many 2s? I feel like Dora. Did you say it out loud? 2 to the power of 9. 2 to the power of 9. Swiper, no swiping. We could go ahead and multiply that. I mean, if I change my screen share, it might totally hate me or it might work nicely. I don't know, it depends. Yesterday was rough. There we go. I can do 3 times 2 to the power of, I could have just done it, yes, the old-fashioned way of times 2 times, oops, I can't even, times 2 times 2 times 2, but how tedious is that? And then I have to go back and say, okay, I have 1 and 2 and 3 and 4, ugh. Instead, let's just use that exponent notation, which says I can do repeated multiplication. I can keep track of it. Ta-da, 1536. 1536. Hey, this is working so good. I'm gonna stop talking about it. You guys just, it was fun. Okay. So 1536 is that final answer that I can go ahead and plug and chug on in. And got it, 1536. So you guys have this formula down below. We could go ahead and actually like label some of these constants as far as what they are. Reminders mostly more than anything in that like that a sub n, remember he is our, can I just draw arrows? That a sub n, remember he's our nth term. That a sub 1, remember he's just our first term. We have to have a starting point with all these patterns. That r we already talked about is just our common ratio from the page before. N minus 1, well, that's just the n, which term I'm on, take away 1. I mean, those ones hopefully are kind of just self-explanatory. Let me though go ahead and highlight if that helps. That n, whatever term you're getting to, is the same thing as the n up in the exponent of the r. And I should probably just draw an arrow really quickly to that r being the common ratio. Okay, anything else that's weird? Nope, not really. Let's keep going. So if we were being asked to find the 12th term of the geometric sequence, I mean, if I was trying to write this in notation, that would be a sub 12. Remember, subscript is just telling me where it is. I would first need to go ahead and identify, well, okay, hold on. They told me it was geometric, which means it needs to be multiplying, but I see that thing getting smaller, like, don't you? Okay, if it's getting smaller, then I guess I could be multiplying by a fraction, like a 1 over, like a reciprocal. Okay, 96 to 24, not many of us have that, but come on, kiddos, don't we have 24 to 6? Aren't we dividing by 4? Now remember, the common ratio is what you're multiplying by, so dividing by 4 is multiplying by the reciprocal. You can go ahead and double check it. What's 96 divided by 4, or 96 times 1/4? Ah, it's 24. So all of a sudden I have my common ratio. If I have my common ratio, if you need to, go back and look at that a sub n formula, but to get to the 12th term, no big deal. Start at the first term and multiply it by however many 1/4 there are going to end up being as we go. 12 minus 1, it's 11. I'm not going to switch over to my calculator. I already showed you that exponent notation. Just typing in 96 times 1/4 raised to the power of 11. 12 minus 1. Ooh, this is a little bit nasty. We end up with this guy being, if you're using scientific notation, we should at least do a few decimals. Remember, we're getting ready for calculus theoretically. 2.289 all times 10 to the power of -5. Or of course, you could have written that in standard form, which would have been 0.1234. Oops, I said 4 because I was counting and then I wrote 4. Oh, the dilemma. I miss you guys. We would talk about life right about now. Let's see, 1, 2, 3, 4, but then we would get distracted. The age-old dilemma. All right, so we have that done, and we can keep going to our next example. Pause me, rewind me if it was too fast. Here we are, find the indicated sum term. Okay, that's awkward. I apologize. That sum is totally a typo. That should not be there. Let's get rid of that. There we go. Find the indicated term. There we go. Which term? First term. Ew. They gave us the, now check it. What am I doing? Still feel like Dora again. Did you figure it out? I'm writing out the 5 terms and saying, okay, this is the 5th. Okay, this is the 2nd. And who's the guy that I want? The 1st. And the 1st is the guy way back here. Beep. That's the 1st term. That's the guy that I want. And that's the guy that I don't have. But what do I have? I have that 3 came second, and I have that 3 over 64 came fifth. Now, wait a minute. Some of you were like, the 3 stayed the same. So I bet this guy has a 3, and this guy has a 3. So hold on. How do I get to 64? How about 4, and then 16, and then 64? And maybe some of you can even think about going backwards with that pattern. But for others of you, you're like, that was too much. If that was too much, there is a mathematical way of solving this that is not so much just trying to see the patterns and play with the patterns and figure out that if I was to go backwards with the exact same pattern of dividing by 4 pushes me forward, multiplying by 4 would push me back. 12 divided by 4 is 3. 3 divided by 4, 3/4 divided by 4, 3/16 divided by 4. I think that pattern works just by using my affinity for puzzles, basically. But for those of you that are like, yeah, no. Okay, the other way of doing it is that you could have actually set up a little baby formula for a sub 2 and set up a little baby formula for a sub 5 using the page before. You could have said, okay, I'm going to start with my first term, which I don't know. If you guys don't mind, we can just name that x, multiplying by a common ratio that I don't know. Oh, stink. Well, hold on. For a sub 2, that would just be the common ratio raised to the 2 minus 1, which is the 1. But for this guy, I needed to go 1, 2, 3. That was times r cubed. We could have technically set up a little formula and said, you know what? I know that this one, going 1 away from the initial is 3, and going r times r away is going to end up being, actually, nope, that would be 4 away. That's why it gets tricky. That'd be 4 away from the first one. We did it from the second one. That'd be to the power of 4. That would get me my 3 over 64. And then we could have done a little substitution-y thing, like, I don't know, x is equal to 3 over r. And let's go ahead and take that guy and say, yay, let's plug it in, substitution. And then we could have gotten 3 over r times r to the 4th is equal to 3 over 64, and done some reducing of thinking about him as being over 1, and that's 1r. That takes away 1 from him to the power of 4. I could also move 3 to the other side, and that would end up giving me r cubed is equal to 1 over 64. Could you have cubed rooted both sides and said the cubed root of 1/64 is 1/4? Ha-ha! You could have figured out your common ratio. You could have figured out your common ratio and said, okay, so times 1/4 times 1/4 times 1/4. So 1/4 must have been what was going on back here. So how do I undo a multiplication of 1/4? You could have actually done a little baby formula and just plugged it right back in and said, okay, 3 came from taking who times 1/4. Well, all we got to do is multiply by 4. And then we have our x is equal to 12. That is one way. There actually is one other way, and it's basically making up your own little baby formula. You could have also done, let me try to change the color so it's, let's make it purple just because. We could have also just seen the second term and seen the fifth term and made our own formula to say, you know what, that fifth term will come from that second term being multiplied by r cubed. We could have actually, it kind of ignored that whole, how the normal formula has to start with the first term. Sorry, checking my phone. The normal nth term comes from the very first term, but we don't have him, so we could say, well, you know what? Let's get that laser pointer out. That fifth term could have come from the second and just been 1, 2, 3 jumps, or r to the power of 3. Now we're making our own formula, but based on basically the math that we've already seen. So we could have multiplied by 1/3 to get rid of the 3. That would have gotten rid of that 3. We would have gotten to a very familiar spot in the sense of the problem up above. Cube rooting both sides. R once again would have been 1/4. And then we would have had to use that 1/4 kind of, or very similar to what we did up above as far as trying to think backwards. Anyway, at the end of the day, the first term is 12. It's the only first term that explains what's going on. There is one other part to this section, section 9.3, not just geometric sequences and how they're related and how we can play around and solve for what we don't know once we know the pattern and how it's being applied or what the different pieces are. The other part is a geometric series. So a geometric series, remember these sigma guys denote repeated addition. So if I was to, even before we talk about that formula up above, if I was to go ahead and let's say play with this example, the example being this sigma notation, 0.3, I don't know about you guys, I kind of hate decimals, I like fractions better, but I'll stick with decimals just because that's how this one did it. Remember with sigmas, we plug in the bottom bound, we count by ones going to the top bound. So one's gonna get plugged into that I spot, and let me go ahead and highlight that real fast. That I spot up here first, 1, then 2, then 3, then 4, and go all the way up to 12. So if we were trying to write that out, that would be pretty tedious in that we would have to say, well, 1 minus 1 is 0, so that's a little bit easier. But starting at the next one, I'm gonna have 2 minus 1 being a 0.3 to the power of 1. Or the next one, I'm gonna have 3 minus 1 being 0.3 to the power of 2, or 0.3 to the power of 3. And all of a sudden, you're like, I have to go all the way to 12 minus 1, which is going to end up being 0.3 to the 11th. Like, who wants to plug that into their calculator? So instead, we use our mathematical skills to say, isn't there a pattern in each of these? Every time, aren't you just multiplying by another 0.3? If you're just multiplying by another 0.3, remember that sigma was just a shortcut notation for this big old series. So even though it's written and can be written most times in a sigma notation, technically we can also just think about this as any geometric series. As any geometric series. Now, if you have any geometric series, whether it's written in a sigma or whether it's written what I've circled, that big old long drawn out addition way, we can use a formula to solve for that sum and not have to actually A, type this whole thing into a calculator, or B, try to figure out exactly what this is by hand. I am not raising 0.3 to the 11th power, and neither do you want to do that. Instead, let's try to see if we can figure out how this formula works. So first of all, let's zoom in on this formula and let's figure out if we know the pieces. So this sigma is just, I'm gonna put in parentheses, another way that a geometric series can appear. And it can be found, if possible, if it's a value, it can be found with S sub n. But how can it be found? Well, okay, the pieces are what's over here to the far right, and that's the most important point or part of the formula. So let's review real fast. That a sub 1, we should know him. That's talking about the first term in that series. Now, for us guys, to find that first term, we actually check it. I mean, maybe we could have seen it up here in the sigma if we compared the two together to what's up above in the formula. But we could have also just started writing it out, which is what I actually tell my BC kids when they got to these crazy series things that they have to work with. Just write it out and be like, oh, duh, a sub 1 is 4. That's easy. Got it. You don't have to go like, because to be very honest, these sigmas can definitely look different ways. These sigmas don't have to be written in this exact pattern and still be geometric. So just be careful of like needing or having to go compare it to find that a sub 1. Just start writing it out and say, hey, who's my first term? Got it. Okay, so now I have my first term. We can plug that into the formula, and we will in just a second. But we have some other guys up here. We have these r's, which hopefully you guys are like, oh, geometric. Those are our common ratios, right? But we have one other piece to this puzzle, and I'm going to go ahead and highlight him the same way I did before, that n. Remember that n is just that exact same nth term, or in this case, nth partial sum. Where am I stopping? This could go on forever. I could just keep adding and adding and adding and adding, letting the pattern continue, and just tells me when to stop. So let's go ahead and go down here and see if we can figure out what all of our different pieces are. So that formula, trying to have it so you can still see it up there at the top. If I am trying to, in this example, find the sum, wait a minute, which sum? The nth sum. Depending on your series, I'm really hesitant to highlight the one n I left out from up above, because once again, I did say these sigmas and these geometric series can be written different ways. They don't have to be written in this exact sigma notation or this exact way of writing it. Oh, your honors, can I show you real fast, even just how this one can look differently? For instance, right here, this little bloop, bloop, and I'm gonna erase it as soon as I write it. A sub 1 times r to the, now check it, with exponents. If I'm subtracting exponents, do you guys remember that's the exact same thing as dividing like bases? It is very rare up until this point in your mathematical training. It is very rare up to this point in high school, middle school math that you have ever gone this direction as far as having gone from, wait a minute, no, we didn't go that direction. This is the way we normally go, having an r over an r and subtracting that exponent. What we did instead is we went this direction and said, you know what? It might behoove us, or it might actually help a problem to have it be written this way instead of that way. Ooh, and the Wi-Fi just stopped. Let's see if I can connect back on in. It kicked me out. It might have been like, hey, you fell asleep. It was Netflix's way of saying, are you still watching? But it was my program's way. So anyway, I mean, we haven't done that very often, if at all. We've never really gone backwards, but just saying, even this like standard way of writing a sigma notation for a geometric series, even it can be rewritten differently, which to be honest, could have been like a 1 over r with a sigma of I equals 1 to n of a sub 1 times r to the I. Or actually, you could have also, I don't want to get you guys too confused. Nope, we'll stop. We'll stop. That's one other way of writing it, or two other ways of writing it. Okay, long story short, when we plug into this S sub n, just be careful that you know exactly what that n is as far as how many terms you're adding together. I started to write this out and I saw that I have to the 1, to the 2, to the 3, all the way to the 11th, that's 11, and I have this first guy, which is 12. So I know that I'm adding together 12 terms. So I want the S sub 12, or the 12th partial sum, another way of saying it. I need my a sub 1 from up here in the formula, or 4 up here in the formula, which is just the first term, which we already identified to be 4. I now need to plug into the rest, which is 1 minus my common ratio, which we already talked about up above by me writing it over and over and over and over. 0.3 is that common ratio on top and on bottom. That was messy, I apologize, 0.3. On the bottom, it's just itself. On the top, though, it is being raised to this, remember, this nth power. And so I'm going to go ahead and get that 12 and put it up. In other formulas, it's actually, remember, that n minus 1, but in this one, it's not. And this one is literally just that nth power. And so if we were to solve this by hand, well, we could do more than you probably would think we could do. In that we could actually go ahead and do that 4 times. I could do 1 minus 0.3 is 0.7, which is the exact same thing as 7 tenths. Ooh. And then 1 minus, now the 0.3 raised to the 12th power is the part that it's like, oh, could we do that in our head? Probably not. But I could go ahead and multiply by the reciprocal on top and bottom, which that's going to go ahead and reduce, which is why that guy's gone. I can also multiply him up here, which would end up giving me 47ths times 1 minus 0.3 to the 12th. I know it's not gorgeous, and I know we're not done. I'm going to go ahead and throw it in my calculator to get like a nice answer. But just saying, there is more that you could have simplified than you probably would have thought of. And then I could go ahead and plug in 1 minus 0.3 raised to the 12th. It's going to probably be a little funny and a little weird. I end up with 5.714. Man, I miss you guys double checking me too. Bloop, bloop, bloop. I guess you need to comment on the video if I were to get something wrong. Oh, you know what? I did this last year. Did I actually plug it in? Oh, I'm ahead. And I was a lazy bum and I totally did not solve it. I just said plug it in. Well, we're amazing and we already solved it. Okay, let's keep going because we're almost done. Let's see how much more we have. We have two examples and this idea of infinity. Now, guys, remember, I am doing a lesson on, we still have that idea of infinity. I am doing an entire lesson, which is kind of like 2 days in class. And if you need me to slow down, you are slowing me down by pausing and going back. But it's gonna feel long, I apologize. But it's because it's the full lesson, not the partial. Okay, so I have 56 and I have 72. Gonna go through these ones pretty quickly. Just because, remember, homework help, and you might want to come back and check this out once you're doing your homework. Homework help, that's what this is meant to be for. And technically, this is also meant to go fast so that you guys don't have to sit through a lot of annoying, tedious, like me, waiting for you to answer questions out loud like Dora. So in number 56, this problem, even though it's not written right here, is actually the sigma from n equals 1 to 10. Uh-oh, I have a marker writing on top. I think it's just, yeah, it is. 3/2 raised to the n minus 1. Okay, so as we're looking at this 3/2 raised to the n minus 1, maybe some of you can see that it looks somewhat like, look at your notes, somewhat like the sigma in the formula, but it looks a little different as well, which is why my advice, once again, is to actually start writing this guy out with what happens if I plug in the 1. Well, 1 minus 1 is 0. Anything to the 0 power, just kidding. Anything to the 0 power is 1. Do we need to double check that up here? Did I raise? No, this was 4 times 0.3 to the 0 power, which was 4 times 1. Okay, but this time it's 3/2 raised to the 1. Or I should say 3/2 raised to the plugging in 1. 1 minus 1 is 0. 3/2 to the 0, 1. But I need to keep going because, okay, that's my first term, but as soon as I start plugging in 2, 2 minus 1 is 1. I have 3/2. If I plug in 3, 3 minus 1 is 2. 3/2 squared is 9/4. And now you start to see your pattern that I'm just multiplying by 3/2 again and again and again. They want me to find the sum. They want me to find the sum. Now, really quickly, to find the sum, I need to know S sub what? Because I need to be able to figure out that n to be able to plug into my formula, because that formula from the page before is the a sub 1, which we already found up here, a sub 1 is 1, times 1 minus r, well, we know r is 3/2, raised to the n. That's why I need to solve for n, because my formula is not complete until I know what to raise this r to the power of. And so I need to figure out what my n is. I see up here, and I really hope it's right, I see a 10. I say, can't I just put in a 10? Because that's what the formula seems to say. Let's double check really fast. When I'm plugging in, my a sub 1 was my first term. This was plugging in 2, my second term, plugging in 3, my third term, plugging in 4 was my fourth term. Yes, when I finally get there, when I plug in 10, I will be getting my 10th term. There are 10 terms total. So I can go ahead and put S sub 10 for my formula. Sorry, my 10s. They look like 16s just because of my stylus. But then we could go ahead and solve. And guys, you could plug and chug that to your calculator, kind of like we did in the example before. You could actually do some like 1 minus 3/2 is negative 1/2. But still, we're going to be stuck with a 3/2 to a 10th power that we don't really know. Yes, we could do some rearranging, but eventually we are going to have to go to our calculator if we're trying to get a nice little answer as far as that they would like. But this is one way of expressing and putting into your calculator, but this would have also been fine to put into your calculator. Just my advice to you would be, once again, remember, there is that really nice shortcut that you guys get to use that we've been looking at all year as far as if you want to put in a fraction. I mean, right now this one has a 1 in front. Others, like the one before, had a 4 in front. But remember, you can use that alpha y equals, that cool little fraction thing as far as putting in. Now, can't do multiple fractions, so I'm just going to do that 3/2 raised to the 10th power. Just making sure you guys know how to use your calculator. 1 minus 3/2. PEMDAS, don't worry, it's going to keep that 3/2 together. 1 minus, that division goes first and then subtraction. So everything is legal. And we could get what that final answer, whoa, 113.33. Oh, may as well write it because we got it. But pause this if you need to work on your calculator a little bit longer. But that alpha and that y equals is a great shortcut, as I've been saying a lot this year. And hopefully it's kind of stuck in your head for next year. Okay, so then coming back to our iPad. I apologize, to our notes. We got that final answer of 113.330. 113.330. Now going on down to the next example, this one says, take this like long drawn out version, this long drawn out sum, and write it using summation notation. What that means is, can you take this and put it into a sigma? Now, if you guys have been noticing, we've been doing like n equals 1 to some sort of, oh, I'm gonna just leave a highlighter. I don't know what term this is. I know this is A1. I know this is A2. I know this is A3. They didn't tell me who this is, those little stinkers. They're gonna make me figure out what that n is by myself. Oh dear. Okay, well, we'll get back to that in a second. But for right now, hold on. What do we know? From the formula, if you need to, look in your notes or scroll back in the video. We have this summation. One way of writing it is with a sub 1. We need that n eventually. We'll get back to him in a second. A sub 1 times r to the n minus 1. So what we need to do is look at what we have right here and say, okay, a sub 1, haha. Okay, a sub 1, I have n equals 1. Always start at the beginning. I have my first term being 32. Let's throw him in. And then I have common ratio. We haven't really thought about common ratio, but common ratio says you're multiplying by something, the same something over and over again. But if you guys notice, this is going down. If this is going down, well, hold on. Is this going down by subtraction? No, wait. If it was going down by subtraction, there's no way I'd be getting a decimal here. If I subtracted a whole number, I get a whole number. So that doesn't work. So division, huh? Division, huh? It looks like minus 6, but that wouldn't get me 10.125. Okay, division. So remember, the common ratio can be found by dividing a latter term by a previous term, and it should always be the same thing. 24 divided by 32, 8 goes in 3 times and 8 goes in 4 times. 18 over 24, 6 goes in 3 times, 6 goes in 24 4 times. Oh my goodness, there is a common ratio, and that common ratio is 3/4. Raised to the, okay, now it's time for me to actually figure out who is this n? How high do I go to get to that 10.125? Well, some of you are like, I can go on my calculator and I can do 18 times 3/4, which is 0.75. I can say, okay, well, that's 13.5. That doesn't work. Times 3/4, 0.75. Aha! I've figured it out. You really just needed to, by continuing on the 3/4 pattern in my calculator, I only needed to go twice. And so if I only needed to go twice, this must be the 5th partial sum, or going up to the 5th term. But be careful, isn't it n minus 1? Which would end up actually giving me the proper sigma notation of n equals 1 to 5 of 32, the first term, times 3/4, the common ratio, and 5 minus 1 is 4. That would be our final proper simplified sigma notation, or at least our version. There are different ways of writing that. But some of you are like, well, you were able to do that in your calculator. What if this was something that was 20, 50, 100 terms down the line? Like, that would be so much work to have to keep count in your calculator. So there is one other way. Let me change colors just so you guys can maybe see it. That other way of solving this would have been, what term is 10.125? We could have set 10.125, that's a 10, not a 6, equal to, we could have thought of it as an a sub n and plugged it into our a sub 1 times r to the n minus 1 formula of, I know my first term is 32. I know my common ratio is, sorry, not 1/4, but 3/4, and I need the n that will make this work. I could have done 10.125 divided by 32. To move that to the other side, I would have had 0.3164, etc. The problem is, to solve this, I would have had 3/4 raised to the n minus 1, and you guys might have, or might be thinking now, wouldn't you have needed a logarithm? Wouldn't you have needed a logarithm? to bring this down and then solve? And the answer is yes. We would have had to have gotten n minus 1 down and by itself by division with that ln of 0.3164, etc., all divided by that ln of 3/4 or 0.75. We would have had to do ln to bring n minus 1 down, divided the ln of 3/4 to the other side. Man, it would have been messy, but we also would have gotten it this way. We just shouldn't have rounded because n needs to be a whole number. And so you would have had to have kept this guy, let me make it nice and clear, dot, 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 kept him that long kind of messy version of 10.125 divided by 32, bringing that to the other side. You would have had to have kept that long old version of that decimal in order to have gotten it to be 5, or at least really close to 5. But you would have eventually, plugging that in, gotten n equals, that's way too thick, I apologize, n equals 5, which is what we filled into our sigma notation. All right, that was a little bit messy, won't lie, but now there's one more big idea, and this is actually the big idea that the Vi-Heart video is really helpful with, and it's a really good lead into calculus as far as something called LIM, limit. Limit is this idea of getting closer and closer and closer, which you could be getting like closer and closer to a fixed object, like here's 5, let's go to 4.9 and 4.99 and 4.999 and 4.999, that's getting closer and closer to 5. That's one way of taking a limit. Another way of taking a limit is to have my x or my value get closer and closer to like an infinity, which is something I can never reach, but I can go to 10 and 100 and 1,000 and 1,000,000 and 10 million, or to negative infinity, -10, -100, -1,000, -10 million. So one way, one idea of a limit is getting closer and closer and closer to, and the other way is just heading that direction and keep on heading. But both ways are approaching, both ways are going closer and closer to a fixed point, closer and closer to infinity or negative infinity. That's a big idea in calculus, this idea of when you get closer and closer to a constant or closer and closer to infinity or negative infinity, what's happening to whatever it is that you're approaching in? Is it converging to an answer? Is it diverging away from any constant answer? Ooh, some good words, convergent and divergent, like the book series. Anyway, I feel like I'm really far away, but that's okay. There's a lot of topics that are kind of introduced in this paper, which is why there's one other ed puzzle. It's a Vi-Heart, it's not me, it's way more fun, way more interesting, and we'll show you a new way to doodle and be distracted in class. To be distracted with all the free time that you have on your hands at home. Haha, there you go, that's a fun way. So what's weird, what's different, what's new? All of a sudden, we have an infinity, which nicely done in this day and age and in this culture with what's going on. Infinities are present everywhere. Like it's actually like a pop culture sort of idea as far as infinities being present. For some reason, this isn't showing up. Let me try to get out and get back in. It kind of just started freezing on me, so let me try again. But infinities are showing up. Maybe someone else is finally using the Wi-Fi. Oh, I didn't welcome it. That's why it's mad at me. Now I want to go. Please? There we go. Okay, so that infinity is that top bound, which is weird, which is different because that top bound is where we stopped. That's how we knew, okay, whew, man, we added 100 of these together, but we're done. This infinity says you're never done. Wait, so if you're never done, what happens if you add and add and add and add and add? If I add 3 and add 3 again and add 3 again and add 3 again and add 3 again, what's happening to my sum? It's getting bigger and bigger and bigger and bigger and bigger. What happens if I add a half and a half and a half and a half? Okay, it's getting bigger, slower, but it's getting bigger. What if I add 100 and add 100 and add 100? Once again, it's getting bigger, slower. Oh, some of you are like, what if you add -5 and another -5 and another -5? Okay, it's still going to be diverging or just going forever to the negative infinity direction. But what happens if you add a half and then a fourth and then an 8 and then a 16th, and then a 32nd. Sum of infinite geometric series. We're not adding the same number over and over again like an arithmetic one. If it was an arithmetic sequence that was infinite, it would be infinity. It would be continually forever going either to positive infinity, getting more and more positive, or negative infinity, more and more negative, sometimes faster, sometimes slower. Calculus is the math of rates of change, movement, but it would still be diverging because it would be going to infinity or negative infinity. But with geometric series, there's something special that can happen. Now, if I add 2 and then 4 and then 8 and then 16, it's getting bigger and diverging again. If I add -2 and then +4 and then -8 and then +16, oh, that's confusing. If r is negative, it flips back and forth. We call it alternating in math. We won't talk about those today. But the big question is, what if we're adding smaller and smaller, I need water, and smaller numbers, or smaller and smaller and smaller negative numbers? Is there something special that can happen? If you haven't watched the By-Heart video, now is a great time to pause and go watch the By-Heart video, the other Ed Puzzle one. That's exactly what I would do in class if I could, but it's a little too hard for me to try to do, and I think Ed Puzzle doesn't like cut in videos, etc. Now would be a great time. Otherwise, just finish up with the notes and then go check it out. Has to do with doodling. Come on, it's fun and it's by heart and she's nerdy and it's great. But I'm going to keep going with the math. So let's go ahead and talk about the concept, and I'll try to illustrate it for you. As far as right now, this says the sum of infinite geometric series, either a sigma with an infinity on top or a geometric series that just keeps going, plus ... never ending. Doesn't exist. Okay, so sometimes it doesn't exist. Like I said, if you keep adding, you add 2, then 4, then 8, if 2 and then 2 squared and then 2 cubed and then 2 to the 4th, it's just going to get bigger and bigger and bigger. If you add the other way, it just gets weird. But if you're adding bigger and bigger values, it's just going to get bigger and bigger. That's what it is. And we call that a non-existent or a divergent series. In this specific context, a divergent geometric series, which is always going to happen when you have r being, and I'm going to put the magnitude of r, we're kind of used to this absolute value notation, when the magnitude of r is greater than or equal to 1. If I'm adding 2, if it's staying the same, 2 is staying the same, 2 is staying the same, times 1 times 1 times 1. If r is 1, you're just adding the same number over and over again. It's growing. Either growing in a positive way or growing in a negative way, but either way it's growing. That's going to be a divergent sum, a divergent series, we would say, because the sum would be infinite. That would be divergent if r is equal to 1. If r is bigger than 1, if r is 2, everything's doubling. If r is 3, everything's tripling. If we are tripling an initial term or doubling or quadrupling, it's just going to be adding bigger and bigger values. That will be a divergent sum. The sum will just forever grow in a positive or negative direction. But there is another case, and that other case is right here. What if I have, and I'm trying to somehow make this stand out, when will the infinite sum exist? The infinite sum will exist when I have r being not bigger than or equal to 1, which means, in context, first of all, I can say this is convergent, and we put right below the sum converges. And I will have a convergent series, that's the adjective, converges is the noun, when my magnitude of r is less than 1. Now, in layman's terms, how could we put that? We could say, oh, absolute value less than 1, that means those little r's are between 1, positive 1, I should say, between 1 and between negative 1. If my r's, if my common ratios are ever taking terms and cutting them in half, cutting them in thirds, cutting them in fourths, cutting them in 3/4, cutting them in 9/10, cutting them in negative 24/25, it's so close to 1, but still I will have a convergent sum. And not just any convergent sum, I will have a sum that converges to this down below. The sum of the infinite series, I got a little messy, I apologize. The sum of the infinite series S sub n can be found by the following. Now careful, if, I'm reading to you my cursive in case you don't get it, if it exists. If it exists, which it might not. If it exists. If it exists, which up above says when it exists and when it doesn't based on the values of that common ratio. If it exists, so I'm going to put 4, absolute value of R less than 1. And if you guys want, once again, you can clarify for your brains, R is between -1 to 1. If it exists, if the ratio is less than 1, sweet, I can plug in by, let's go ahead and label things again. I have my A sub 1, my first term. I have my R, which is my common ratio. And as we talked about before, wait a minute, S sub n, hold on, that doesn't make sense because S sub n tells me when to stop, and the whole idea of infinite sum is I'm not stopping. So wait a minute, I shouldn't have an n there. I'm gonna do the weirdness up here on my, I have to go find a white marker. I'm gonna take out this n because technically there is no stopping point. If there is no stopping point, well, wait a minute. Any of you smarties out there thinking about what I could put there instead? If I'm not gonna put an n, if I'm not gonna put a number, could I put, oh, that's messy. Could I put an infinity? Could I put an infinity? And the answer is yes, I could put an infinity, except that's not proper in math. In math, we don't put an infinity in a constant spot. Now, I know. Up above in the sigma, there is an infinity up there in the constants spot. But actually, in higher math, we have to think about what that really means because infinity, and you can talk to some of the BC kids, David Park especially, infinity is not a number. Infinity is a concept. It's an idea. It's this concept of ever increasing, ever expanding, ever getting bigger. So actually, if I was to write this in a very proper way, you're allowed to keep it like this. It's not awful at this level if you do. But if you wanted to write it in a calculus way, and this is where the limit, the LIM notation comes up, we would technically have to say, okay, we are doing S sub n, but we're doing S sub n in a way that, wait a minute, there was a formula for S sub n. The formula for S sub n was this one. And then I had this from the page before. I need that n to not be a set number. I need that n to be ever getting bigger. And I need for me to figure out what that value, what that sum, as I have 10 terms, 100 terms, 1,000 terms, I need to figure out, is that getting closer and closer and closer and closer and closer to a set distance? Is that converging upon a set sum? The answer is yes, once again, if it exists, if that R, magnitude of R is less than 1, if that R is in between 1 and -1. The answer is yes. And so the answer is technically that formula that you guys see up above, that A1 all over 1 minus 1 minus R. But if you want to know why, the reason why is because technically we're using this formula that you guys talked about before. But when we plug in one of those special R's in between 1 and -1, and when we raise that special R to a higher and higher and higher power, meaning n is 10, n is 100, n is 1,000. If we're looking at this, the only thing that is changing is this n is growing, is getting bigger and bigger and bigger and bigger. You guys go in your calculator and plug in any R in between 1 and -1, not 1, not -1. Raise it to the 10th, raise it to the 100th, raise it to the 1,000th. You're going to see that this, ready for a new notation, this always, any R in between 1 and -1 raised to higher and higher powers will be getting closer and closer and closer and closer to 0. And this idea of a limit in calculus says we can see what's happening. We can follow the trend and we make the jump and say, oh, 0.000000, you're going to 0. Boom. And you can plug in 0 for that value. And man, 1 minus 0 is just itself. And that's technically where this formula up here comes from for any convergent, once again, for any convergent geometric series. We're going to practice that just a little bit and be done. Check out that by heart video, please. So in this guy, it's weird. There are 2 different ways of showing infinity in these 2 different examples. This one puts an infinity up here on the top, and this one puts a ... that never ends. Both of them mean infinite, which is seen in the directions up above. So as we go to solve this, if I were you, I would just start plugging in, especially when zeros show up instead of ones. But if I plug in 0 to the n spot, Anything to the 0 power is 1. 4 times 1 will just be itself. And then I have 4 times 0.2 raised to the first. And then I have 4 times 0.2 raised to the second. I could do this all day. And the point is that I should, because it's infinite, ... So I can't literally put this in my calculator and add it. But what I can do is say, hold on, does this infinite sum exist? Is it convergent or is it divergent? How do I know that? I have to look at my common ratio. Guys, what are you multiplying every time? Dora, did you answer? 0.2. Is 0.2 within or in between -1 to 1? The answer is yes. Since -2 is in between 1 to -1, what can I say? I can say this is a convergent one, since r equals, if I was writing it out, 0.2, which is less than absolute value, less than 1. Since that's true, I do have the sum. And the sum will be, I'm teaching you some calc-easy stuff right now with using words and explanations and justifying. The sum is a sub 1. Who's the first term? A sub 1 is right here. 4 is a sub 1. Well, there's a few different ways of doing it. You can do a sub 1. Let me show you right here. A sub 1 times 1 over 1 minus r. You could do that way, which our r is 0.2. The other way of doing it is you could always just see, you know what, that's always going to be a sub 1 over 1. So I can actually rewrite this formula and say, psh, why not just do a sub 1 all over 1 minus r? Oops, I did the 1 minus r in my head. So this is what our little formula on the page before would have said. Maybe a better way of writing this formula, a simpler way, even though this isn't wrong, would be a1 all over 1 minus r. That's what the majority of Calc BC kids use. It's just a little easier usually. It does have complex fractions sometimes, so be careful. Oh, I have a complex fraction right here, because if I go to solve, let me get rid of this book's version of the formula. 1 minus 0.2 is 0.8, but isn't 0.8, ready? Isn't 0.8 the same thing as 8/10, and 8/10 being divided is the same thing as 10/8 being multiplied? That's going to end up being 5. If you were to go in your calculator and do 4 plus 4 times 0.2, and then plus 4.4 times 0.2 squared, and then add another, and then add another, and then add another, if you were to put that in your calculator or your table and then try to solve, you would end up seeing that it was getting closer and closer and closer and closer to 5. Maybe 4.75, 4.9, 4.99, 4.99, it's converging to 5. So we say 5 encapsulates. If I could go to infinity, I would get to 5, which is a really weird thought. But 5 is at the end of infinity? Well, only for this problem. God is at the end of all infinities, I think. But 5 is at the end of this infinity. And then we have one more problem, and then I believe we are done, because that limit notation I've already kind of showed to you. There might be a homework help that wouldn't be great, but I know this is taking long. So remember, 2 days cut into 1. But with this one, as we're trying to solve, let me just do it quick. Our a sub 1, great thing is they already gave it to us, so we can already write that out. If we were to try to figure out what our common ratio is, maybe you guys notice that every time we have 1 less 6, 36 divided by 6 gets here, and then 6 divided by 6 is 1, and then 6 times 1, And then here, I'm getting rid of a 5 every time. So how do I get rid of a 6 from a denominator? Well, I must have a 6 in a numerator. And how do I get rid of a 5 from a numerator? I must have a 5 in the denominator. You could have also used your little, it's going to be mad at us again, just because, why not? It's getting tired, I do believe. There we go. It's telling me to stop. I'm close. R equals 6 over 5. Oh, you could have also used your, I need to get back on track. You could have also used your a sub 1 over, a sub n over a sub n minus 1. Oh, but that's a negative number. Is this a negative common ratio? Oh, my signs are alternating. If I multiply by a negative, I get a positive. Multiply by a negative, I get a negative. Multiply by a negative, I get a positive. Oh, it's a negative. But guys, the long story short, is this less than absolute value? So it's a positive. Is this less than 1? The answer is definitely not. since this is not less than 1, since the common ratio is not less than 1, it's greater than 1, but I can just say greater than or equal to 1 because all of those fail. This series is, do you remember the adjective? Divergent. And I can say, so the sum of the infinite series does not exist. What is it? That's not the question that we're answering today. We'll just say the sum does not exist. We did talk about this idea of the limit. Now, I usually put my L. There's some TikTok out there. I forget who was showing it to me, but how like instead of doing a T this way, you do a T that way. Instead of doing like a 2 or a Z, you got to put that line through it, or maybe you do a 2 like this. And instead of doing L, you do L. Anyway, I totally agree with that. I do a cursive L because I like it because it's prettier. That is not by any means like every mathematician has to. It's just we're lazy and we're tired of misreading what we're writing. So I do a cursive L for my limit. But what is this? If the limit is as n approaches infinity of s sub n, that's just a snazzy way of rewriting, going from n equals 0 or 1, could be either 1 to infinity of, just kidding, not s sub n, a sub n would be in here. That's just a snazzy way of writing that, of an infinite. And another way of writing that, what else it also technically means is a sub 1 plus a sub 2 plus ... plus a sub n. You don't stop though. Don't stop believing. Anyway, really cool calculus notation. This is your introduction of how do you go to infinity with a limit? How do you know if there's an answer? The question is there convergence? Anyway, moving on. The last example, and then we're finally done. This is just a weird homework help, and so I just want to show it to you quick. Repeating decimals and rational number representations is a great application of infinite geometric series, because if I was to write this out, this would take me forever, literally, right? 3, 1, 8, 1, 8, 1, 8, 1, 8, etc. But another way of writing this is that this is actually 18. Well, okay, it's a little weird to think about, but 18 over, isn't that in the tens, hundreds, thousands place? And then this next 18 could actually be 18, but instead of tens, hundreds, thousands, 10,000s, 100,000s place. And then this one, because I'm running out of zeros, this one could be, wait a minute, you're just adding 2 zeros every time. So that would be 1, 0, 0. There was 3 to begin with, and then I added 2 more, and then 2 more after that. 1 10 millions, and then, oh my goodness, there's a pattern. This is actually 0.3 plus 0.3 plus. And what it's being added is what we would call a geometric series of 8 1,000s plus, 18 1,000s all over 18 100,000s plus 18 10 millions. Do I have enough zeros? Nope, one more. And I'm going to put my plus ... I could talk about this as a geometric series and say, hey, I have my a sub 1, and I have my common r of 1 over 100. I'm moving 2 decimal places every time. And I have my, this is less than 1, so this is convergent, and not only convergent, but it converges to what fraction? A sub 1 over 1 minus r, which I could say is that first term, 18 over 1,000, all over 1 minus 1 over 100, which, isn't that just 99 over 100, 18 over 1,000? Can't I divide by a fraction by multiplying by the reciprocal? That's going to go away. 2 of those zeros are going to go away. My 18, 9 goes into that 2 times. 99, 9 goes into that 11 times. 2 goes into that remaining 10, 5 times. I believe I end up with 1 over 55. Now, wait a minute. What is 1 over 55? 1 over 55 is what this portion of this fraction was. So I end up with 3/10 plus 1 over 55, which would be, common denominators, gross. Well, Let's just change this guy to be to 55 and this guy to be 10. I'm going to end up with a common denominator of 550. And I have 1 times 10 is 10, and 3 times 155 is 165, 175. Oh, I can reduce that. 175 over 550 ends up being, well, 5 goes in. Well, 25 goes in. So 175, I'm being lazy and tired. Sorry. 4, 5, 6, 7. 7 25s go into that one. How many 25s go into, okay, how many quarters are in $5.50? $5, 5 times 4 quarters, each dollar is 20, and then 2 more, 22. Oh my goodness, what is 7 divided by 22 in my calculator? 3.181818182. Okay, I have to show you this. 2, the only other page is homework. 2, why is it 2? Hold on. Oh, wait, doesn't our calculator only have the capability to hold in so many decimals? So wouldn't that be if it was a 1/8 rounded? With geometric series, you can now take any repeating decimal you were ever given and find the fractional equivalent. You're welcome, Infinite Series. Watch the by heart video. Love you guys. Hope you're doing well. Come find me in an online math lab member during class time any day, and I will talk to you later. Bye. Oh, I'm still here.